if I have a Borel measurable map, okay, we have an abstracted space in the Borel measurable map F, such that f of x is equal to the probabilities of this Borel set. We call such an f as the probability density function, distribution function actually. While probability density function is what? It's any Borel measurable function such that its Lebesgue integral is equal to 1 actually. Okay? This would be the key thing. And if this would be the case, then I can, so in other words, if this, so for a given measure, if there exists such kind of a function through which you can compute the probabilities, then you call such a measure as a continuous measure in some sense. Okay? So that's one of the things. Do we have an example of density function? I mean, if you read the book, there are lots of examples. I'm not getting into all that. Okay? I mean, there are lots of examples that the book is giving related to finance. I mean, if you wish, you can read them. If you wish, you can leave them for more actually. Okay? What would be the example of such kind of a function? So just simply take, the PDF of a normal distribution x square over 2. Let's not see this as a PDF of a normal distribution, but just let's see this as a function. Okay, then it's a continuous function. Okay, it's a continuous function which is defined on whole R and hence Borel measurable.
So root pi over 2x over
2 pi, yes. 2 pi. Okay, then it's a continuous function which is defined on whole of R actually. Okay. Now, if I compute the Lebesgue measure, okay, of this function, the integral of this function,
same as
over,
it's same as Riemann.
then it is same as Riemann integral.
Because there is no discontinuity.
R, and this will be, f of x dx, and this is known to us that this is not
Normalized.
So we have done it actually.
You said.
We have proved it actually. So that would be an example of. So there are lots of examples given there. So what we have defined abstractly what we mean by a density function and what we mean by a distribution function. Later on, we're going to define the same things, but relative to a random variable actually. Okay, we haven't given reference to a random variable yet. Okay. What is the next thing that I would like to do? I would like to prove some properties of distribution functions. Okay, now I'll not prove just all, I'll just prove two and the rest you can read it for yourself. Like these are the things we usually ignore actually when we do, so we just take them for granted. But what I want that at least for once you must see their proof that why they are true actually. Okay? So here's a little theorem which says that imagine if you have a distribution function, so let f be a distribution function, and by distribution function it's a Borel measurable function from R into the interval 0 to 1. Okay, distribution function. Then f has following properties. Number one, if f is non-increasing, in other words, f of x is less than or equal to f of y for every x less than or equal to y. So this is a non-increasing function actually. F is non-increasing, okay? First thing,
Non-decreasing.
non-increasing. Non-decreasing function. Non-decreasing function. Okay, it's increasing function. And it's right continuous. So in other words, if you have limit x goes to a, from a plus f of x is
F of a.
f of a. It's not necessarily continuous because it's not necessarily left continuous. We can see why. And if you have limit x goes to infinity, x goes to minus infinity, have a guess what you're going to get?
0.
You're going to get 0. And the fourth is that if you have limit x goes to plus infinity,
1.
f of x would be whole one. Okay, so this is what the key properties that I want you to do. So I'll just prove 1 and 2 for 3 and 4, just read the book. Okay, so just do them for those subjects, that would be an exercise. Why the first property is true? Okay, so if x is less than or equal to y, obviously the interval minus infinity to x is contained in the interval minus infinity to y. Okay?
And hence measure
And hence the measure
subset.
of minus infinity to x is less than or equal to the measure. Okay.
Minus infinity to y.
This should not be included. Obviously. Less than or equal to the probability measure of minus infinity to y actually. Okay, so it's like a subset of b, then probabilities are included actually.
Okay, f of x is less than
This is obviously mean that f of x is less than or equal to
f of y.
f of y actually. Making it simple. So it's a trivial exercise, easy exercise, but I want that you should do the proof. This is important. And keep these properties in head. Distribution function always increasing, right, continuous, and so as x goes to minus infinity, f of x is 0, and x goes to plus infinity, this is 1 and 2. Okay. What would be the proof of the second thing? Imagine, huh?
Take on the line theory.
Yes, so let xn be a sequence of, so non-increasing sequence of real numbers. Simply non-increasing. What's it? Kind of decreasing actually.
Converging to a.
Increasing sequence such that limit n goes to infinity, xn is a actually. Okay? Where each of the xn is bigger than a. Alright? So it may be a. Okay, so how do we prove something is right continuous? From real analysis actually. Okay? Mind from real analysis. When f is continuous actually. So we said that when the limit exists, not continuous, when the limit x goes to a, okay, so we left out from right, is equal to f of x is equal to L. So give me a precise definition. So in other words, if I want to prove this, what I need to do?
For every epsilon
There exists a capital N.
Okay. That's one way to do it. But we also define convergence in the terms of the sequences. So in other words, if I have any sequence which is bigger than a and it converges to a,
and applying for
okay, then f of xn would converge to f of a
preservance.
as n goes to infinity. So somehow this function f is preserving the convergence, and hence we have the continuity. So that's precisely what I want to do here. So I want to prove the right continuity. So I want to take a sequence which is on the right of the point A, and then I want to show that okay. Okay. So that's a definition. Okay. We need to keep these definitions in our mind. Okay. So imagine I have a sequence in which every term is bigger than A that converges to A. Then this interval minus infinity to A can be written as, how can I write it?
Sir, x and x to a.
Sorry. So in other words, what would be the relationship between the sequence, like a minus infinity to A, and the sequence so the sequence of intervals which I formulate, for example, through this xn. Would that be union, intersection, or what?
Intersection.
It must be intersection and equal to 1 to infinity.
Right,
It should be
Yes, sir.
intersection, okay? And then, what I need to do, let's compute the probability.
Sir,
Uh-huh.
we are using assumption xn is greater than a for all n.
So this is true for all n, obviously. So when I haven't written it, it should be,
Now arbitrary intersection is equal to that interval.
I'm sorry?
How arbitrary intersection of that minus infinity to n equal to minus infinity to a.
Uh-huh.
So equal with everything.
No, I mean, you can, okay. So it's like, so one of the things that you can do, good exercise, take an element from here, show that it's here, and take an element from here. So
Say pictorial
pictorially भी देख सकते हैं, make sense.
infinity xn is equal to a.
Okay.
Infinity xn is a.
So if you have this equality, then their probabilities would be same. What do you can say? So if x is non-increasing, what do you can say about the sequence of these intervals? So it's like, what would be the relationship between minus infinity to x1 and minus infinity to x2?
x1 वाला contain होगा minus infinity to x2 वाले.
Limit n to infinity after that will.
No, that would be a kind of a decreasing sequence. So you can say that,
x2 is contained in x1.
yes.
ठीक है. Subset wise.
And if you have this, then I have a result, we proved it, that if you have a
First class.
probability of intersection of decreasing sequence of some sets, and this is same as limit n goes to infinity, okay, of the probability of minus infinity to xn. Okay. Now this guy is what? That's your f of a, and this is what? Limit n goes to infinity, f of xn. That's precisely what you needed to show. So it's like f is preserving the convergence. So if xn is a converging to a, then f of xn is converging to f of a from right. Okay. And this is a very useful definition. Okay? We learned this in function analysis. We did this in real analysis, and so on and so forth. So try to do something similar for these two problems. Okay, so these are the very basic properties of PDF. So far we haven't used or defined or used random variables anymore. So these are like the pure properties of the functions that you have defined in the terms of the in the terms of the measure actually, or in the terms of integral of a Lagrange measure. Okay, but now I'm going to define them. So let's bring the random variables. So I'm just following the bookish pedagogy. Otherwise, I could have started from random variable. Okay, so random variable is this, and then doing the rest of the things in the terms of the random variables. But okay, let's not complicate your life. So what's a random variable? So I have a probability space omega fp. Okay. So a map from x from omega into r is a random variable. Okay. If x is f measurable. Okay. By f I mean a graphic f. F measurable. Okay? And what is the meaning of F measurability? That is, that if you take any Borel set, okay, and compute its x inverse, that belongs to F. Okay? For all Borel sets. Okay? I can make it, okay, I can show that, okay, like this is a too strong condition, I can make it weak by just showing that, okay, if x inverse of some open intervals, so if this is true for all open intervals, still x is measurable. So I can show that x inverse, or you could do a good exercise to show that if x inverse of, so like this condition is equivalent to saying that x inverse of each open interval, where open interval is some, Borel set.
Because we can approximate this.
Because every Borel set can be written in the terms of
Open sets.
open set. So if this is true, then this must be true as well. Okay. By the way, this is the this is a notation that probabilists don't like actually. So whenever they want to say this, they will say this x belongs to B. What does this mean? Okay, let me write it precisely. What does this mean? This means that this is a set of those omegas for which the x of omega belongs to the Borel set. Okay? Alright? And this is precisely what this means actually. What is the meaning of x inverse of B? So it's a collection of those omegas for which x of omega belongs to B. Okay? So since this can be written as this, so whenever they say this, they mean actually this. Okay. And I have said it several times, even if this is the case, think about it. Previously, when you are writing, okay, what is the probability that x is 2? So you say that 1/4 actually. But we know, I mean, is this something which is well defined? Unless you give it a meaning. Think about it. Let x equal to 2. We know that probability is something that works on a set actually. Is this a set?
Huge confusion.
We know that that's an equation actually. So what is the meaning of applying a mathematically probability measure over an equation? But I can interpret it. So when I'm saying x equal to 2, it's not really x equal to 2. It's a collection of those omegas from omega for which x of omega is 2x. So that's what it means. So they say that, oh, who gave tuned it, but let's directly write it like that. Okay. So I'm fine with this notation. I mean, it's completely okay. But I'm saying that you should know this, that there is this is sitting behind it. That's what it means practically in mathematics. Okay? Because we know that probability measure is a map from sigma-algebra into the set. Are you getting the point? Let me define. So we have seen what is the meaning of sigma-algebra generated by a set actually, or maybe a collection of sets. What is the meaning of a sigma-algebra generated by maybe A naught? A naught is some collection of sets. What does it mean?
It's the intersection of all those algebras
Containing an
in which this set is contained.
Okay, that's one way to do it. But the other way to do it is that basically every element in this sigma algebra can be written as the union of elements from A naught actually. That's what always also means. Sigma algebra, sigma A naught is what?
A naught works like a basis.
It's like a basis. Shouldn't call it a basis.
In some sense.
In some sense, intuitively, yes. Okay, so it's a collection of all such B's, such subsets of X or maybe omega or whatever you have set, such that B can be written as the union, okay, an countable union of the elements from A naught. This is what that means. Alright? And maybe in Fourier for the sake of your satisfaction, you can try to prove that if this is sigma algebra. Okay? Anyway, so this is not that I want to do. I want to generate a sigma algebra from a random variable. Okay? What is the meaning of generating a sigma algebra from random variable? I want to, okay, obviously I know that sigma algebra is all about sets actually. It's all about sets. So what it has to do with the function actually? So can I associate some kind of a sets with this function?
Range of x.
Not the range, but the better would be if I say that sigma algebra is so that a sigma algebra generated by the random variable is a sigma algebra, okay, generated by the sets of this kind set. Sets of this kind. So what does this mean? This means it's a this set is a collection of all sets which contains the inverse images. So in other words, if I write it precisely, at least for once, that this is the converse. So this is a sigma algebra generated by the inverse images of under X actually, okay, where B is the Borel set. Okay? Are you getting the point? Or I can break it down, I can say that sigma algebra generated by the random variable means sigma algebra generated by the X inverse of the open intervals with the open intervals of Borel. So this would be another thing actually. Because the way open intervals and Borel, sigma algebra elements are related to each other. Okay, are you getting the point? Okay. I'll send you some exercises in which you will have some particular discrete random variables, and your task would be to generate a sigma algebra. At least you should do some examples related to that. Are you getting the point? I can even generate a sigma algebra from two random variables. What would be that? So that would be the sigma algebra generated by the collection X inverse of B, okay, where B is from Borel sigma algebra, union Y inverse of B, where B are from Borel sigma algebra. Something trivial. Is it making sense? And I can go on. But let's just stick with this. The sigma algebra generated by the random variable X. Obviously, you can prove it that this is indeed a sigma algebra. Okay, this is indeed a sigma algebra. We can prove it easily. It's not a big deal. Okay. By the way, we can also show that sigma algebra generated by X is contained in F. Okay? So here are some exercises. So number one. Okay. Forget about this, for example. This is a sigma algebra. Yes. Such that the sigma of X is contained in F. Do I need to prove? I know that all these are in F actually. So, at least showing this part is easy.
Sir, वो जो definition है intersection करते हैं वो नहीं apply करते हैं जो भी define किया है इस definition the definition we have defined for generated. So we will follow this one. So previously we had intersection of all sigma algebras.
Yes.
So it is by default
that definition. But like आप show कर सकते हैं, you can show that empty set belongs here and
In this
all
particular
belong there.
right.
It satisfies the definition. Okay. And it's not really, the next part is not really related to the random variable, but I think I haven't mentioned it anywhere in my lectures. But if I have a collection A, which is, if I have a collection C, which is, a subset of another collection D, where all these are the collection of 2 to the omega, okay, the collection of subsets of omega x, whatever, then sigma algebra generated by C is contained in the sigma algebra generated by A. So this is what you have to show. And the third, I want an answer from you. What would be the sigma algebra generated by a sigma algebra? The answer is that it would be the sigma algebra itself. Why? Just think about it. Because it is the intersection of all sigma algebra that contains this sigma algebra. Then the smallest sigma algebra that contains this sigma algebra is itself. So like these are some facts, which will be used at random places. So always keep in mind. Another exercise, or maybe I gave this an exam as well. I said that if H, or a version of it, if H, is Borel measurable, so in other words, it's a map from R to R, and it's Borel measurable, okay, R to R. It's a Borel measurable map, and x is a random variable, then H composition x
Is Borel.
is measurable. Will that be Borel measurable?
We also know that X is Borel
Measurable. Measurable not only with respect to f, because that would be a trivial fact, but with respect to the sigma algebra generated by x. And this seems so innocent statement actually. It's so powerful actually. Think about it. So in order to show the measurability, what you need to do? So help me out with this. So x is a map from omega into r. So I need to consider the inverse of this guy and operate it on the Borel set. Okay? And I have to show that whether this belongs to here or not. Okay? So it's going to be x inverse of composition x inverse of b, and since h is Borel measurable, so this guy is a Borel set, and if I operate x inverse onto a Borel set, okay, we know by definition that it belongs to basically sigma of x, so this belongs to sigma of x. It's like a pretty easy and trivial thing. But what's the power of this result? Think about it. Imagine I say that x is measurable random variable, and I say to you, prove that
e power x.
X square plus 2x plus 3 is measurable. Think about it. Like if if I have to do this by definition, I'm in trouble.
Yes, sir.
But this result is telling us that since I can see this as a continuous map and hence Borel measurable operated onto the random variable, so that's also measurable. So this is measurable. Are you getting the point? Is it making sense? So take h of x to be x is